All right, hey everyone. So this is chapter 6, ionic and molecular compounds. Um, I apologize. I tried to do this last night, and when I went back and listened to it, I had all kind of noise in the background and all kind of stuff going on. So I had to wait till today. Um, I did post a bunch of videos on Cougar View. So you don't have to watch all of those. Those are just kind of supplemental if there's something that you don't get as well from the lectures or the book or the PowerPoints or whatever else. Don't be afraid to go on YouTube and kind of hunt out these things and try to get someone to explain it to you a different way. Okay, a lot of colleges is being resourceful and figuring out what's best for you, how you can learn the material that you need to know to be successful in this course or in life or in your job or whatever, right? So a couple announcements. First off, the test. I have a few people still haven't taken the test. Some of it for medical reasons and other extraordinary circumstances, but I'm not going to return those until everybody's taken it. Should it very hopefully Sunday, everything will be turned in, and then I'll post those either Sunday evening or probably more likely Monday. The practice exam was a bonus, and I'll probably just add that straight onto your midterm grade. All right. So far, everything looks fairly decent. If you did like electrons, and the word was electron, you obviously get credit for that. If you get close, if you're like say off by a power of 10, I think you might have just converted something wrong. You probably will get partial credit. So uh, you probably did better than you think. I say all that just say you probably did better than you think. What else? Early voting started. Y'all get out there and vote. Um, be cautious though, y'all. Social distance, wear your mask, all that good stuff. That being said, let's talk about what we got coming up. So, this chapter, like I said, I started a little late. I'm going to give y'all till next Wednesday to get this. I'm going to post another Master in Chemistry this evening, and that won't be due till Wednesday. So, those of you that do your work on the weekends can do that, and those of you that have to do it during the week, hopefully between Monday and Wednesday gives you enough time. Okay? So, ionic and molecular compounds. There's a couple things I want to touch on before we get into this, just kind of review because we hadn't talked about it in a little while. Valence electrons, which is why I posted that video on your Cougar View. This is why it was important that you know what valence electrons were. So now we're going to start using them to do these chemical formulas and bonds and stuff. So chemical bonds, we're going to need to know about valence electrons. So let's kind of revisit that. I also posted your PowerPoint so we can kind of scroll through there and use these as well. So this image will actually work for these purposes. Remember that electrons occur on these little orbits called energy levels, right? And they fill up in a certain way. There's a bookshelf in the earlier chapters that kind of depicted it, where the first energy level can only have 2, and then the next one can have 8. Okay, here it is, 2 on this one, then the next one can have 8, and then the outermost shell is where I find the number of valence electrons. The valence electrons is only concerned with the outermost shell. Okay, so if I look at a periodic table, remember that I can know how many valence electrons there are just based on the group number. So hydrogen in group 1 has 1 valence electron. So does lithium, sodium, potassium, rubidium, cesium. All of these have 1 valence electron. Okay, so it's important that I keep that in mind because it'll allow me to predict other things going forward. Okay, and I'll get to that here in a second. Beryllium, group 2, it has 2 valence electrons. Magnesium has 2, calcium has 2, strontium has 2. All right, now remember you skip across over to boron for group 3. So boron has 3 valence electrons. Aluminum, 3 valence electrons. Don't worry about these metals just yet. They don't quite follow the same rules. Carbon, group 4, 4 valence electrons. Silicon, also 4. So when I draw an atom, let me get my little pen. When I draw an atom, let's say sodium, all right, what we've been doing is doing all the electrons, 2 and then 8 around this shell, 3, 4, 5, 6, 7, 8, and then my valence electrons of this outermost shell, there's only 1. Okay, now for simplicity, we're going to stop doing that. Okay, I'm going to stop right now all these valence electrons, but I want to show you them here just for this reason. What is an ion? Okay, that's also one of your videos that if this doesn't get it across, you can go back and look at that. An ion is something that either gives or accepts valence electrons from another atom. Okay, so in sodium's case, it likes to interact with chlorine, for example, salt. Table salt is sodium chloride, NaCl. Let me write that down right here. Okay. Now the way these two hook up is something called an ionic bond. An ionic bond is where one atom gives away an electron and another atom shares it. So the electron, this little E minus, is going from the sodium, to the chloride. Okay. Now why is that happening? It's happening because of something called the octet rule. I'm going to go to your, I think your text has, show you where I'm at here. Okay, so top of page 169, octet. The octet rule is just saying that atoms want to have 8 valence electrons. Okay, that is the best position it can be in. In scientific terms, it lowers its energy level at 8 valence electrons. That is the ideal configuration for an atom. And so it wants to get there. Sodium wants to be there. Chlorine wants to be there. Every atom on the periodic table, let me go back to that, wants to be at 8 valence electrons. So what does that mean? That means that all of these ones with 1 valence electron, like the sodium that I'm doing here on my iPad, it wants to have 8 valence electrons. Now, is it easier for me to get 7 electrons and add them to this outer energy level? Or is it easier for me to give this 1 electron away and just have this become my outermost energy level with 8 electrons? It's easier to give that 1 away. So that's what happens. The sodium, with its 1 valence electron, will try to find something that has 7 valence electrons, and it can actually do it on others. It'll find different combinations, and we'll get to that here in a second. Chlorine, if I look at my periodic table, has 7 valence electrons, right? It's in group 7. So that's how many I'm putting around this outer shell. 7, 6, 7. Okay, so remember, all atoms want to be at 8 valence electrons. Okay, this one wants to get to 8 somehow, and this one wants to get to 8 somehow. And you got to remember that this one actually has 8 on the inner more energy level. I didn't write it here, but that's because we just established that. All right, so now it's easiest for me to just give this electron to the chlorine. Hey buddy, you have this thing right here. I'll get rid of mine, and now we both fill our octet. Okay, so that's what happens, and this is called an ionic bond, right? So now what the sodium becomes positively charged because it has 1 less electron. You remember us talking about charges, right? So if it gives away that electron, it has 10 electrons total now, and it still has 11 protons, so it becomes positively charged, one positive charge. The chlorine now has 18 total electrons, and it usually only has 17. So that means it's negatively charged by 1. And so we put a little minus above it. We also have names for this. Let me erase all that. The sodium with a plus charge is called a cation. Okay, cat is just for that little plus. If it gives away electrons, it's called a cation. And then the chlorine, which has a negative charge, is called an anion. Okay? Anion is something that accepts electrons from another atom. Okay? Now we said that opposites attract, right? The negative charge will attract to the positive charge. They stay kind of bonded because those charges are opposite. This is what we call ionic bond. Okay? When that sodium gave up its electron, it was really tight to that chlorine already, and then they had the opposite charges, so they stuck together, and then we call that an ionic bond. All right? And so you'll see that occur again and again and again, right? The fluorine, chlorine, bromine, iodine, they all tend to accept one electron from some other source. So you'll see them hook up with sodium or potassium or lithium or hydrogen, one of these other one valence electron atoms. All right? Now metals are a little different. Metals can give up different number of electrons. They don't give up a certain number because there's no easy way for them to get to an octet, right? These down here, when you start passing row 4, they kind of follow different rules. Okay, they can go over the octet in some cases. In others, they don't fulfill the octet at all. So metals are a little different, but treat all the ones on the far left and the far right the same. These ones on the very far right already have an octet, so they don't like being messed with. And for the most part, you'll never see these helium, neon, argon, krypton interact with anything because they have their octet set and they don't want to change. Okay, we call those noble gases. They're inert, meaning that they don't interact or react with other things. Okay, let's go to these slides. Let me see what I'm missing. So this is an example of what I was just saying. The sodium had the electron on its outermost shell. The chlorine had 7, but they wanted to fill their octet, which I don't see it mentioned here. Yeah, here you go. Share valence electrons to acquire an octet of 8 valence electrons. Okay, so now that is the ionic bond where electrons are transferred. They're given away to somebody else. There's also another way we can do this, and it's called the covalent bond. So now we talked about ionic bonds where a charge is formed. Covalent bonds share electrons. There are no charges in that sense, okay? Remember, the charge is essentially what holds these two atoms together, the fact that they're oppositely charged. But what holds two covalent atoms, a covalent bond together, is the fact that they share the electrons. So let's say chlorine. All right, so I'm going to do the same thing I just did where I have the 7 valence electrons around its outer shell. 4, 5, 6, 7. Yep. All right, and then another chlorine on this side. 1, 2, 3, 4, 5, 6, 7. All right, so now is there any way that I can make 8 valence electrons on both of these atoms, right? There is. Okay, what if I bring them so close that they share electrons, right? So I'm going to erase this and these 2 electrons there, and I'm going to make my circle a little bigger, all right? And I'm going to make them interact, and I'm going to say put those 2 electrons back right there. So now count each orbital around each chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Oh wait, 1, 2, 3, 4, 5, 6, 7, 8. Around the one on the right. One on the left. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is a way that I can make the octet, is by sharing electrons. We call this a covalent bond. Notice that each one still has to have that electron in its orbital. That wasn't the case for the sodium and the chloride. The sodium had to get rid of its electron and had to give it to the chlorine and let the chlorine keep it by itself in order for the sodium to have an octet on this inner, which has now become the outermost shell of the sodium. But in the covalent bond, they're sharing. And so those electrons technically still belong to each of the atoms. We call this a covalent bond. There's also another way of writing it, which is this little line like this. So if you see one of these lines, you need to remember there's 2 electrons in every one of those lines. All right. And then if I fill out the rest of the valence electrons, this is called a Lewis dot diagram. We'll get to this. I don't know if we'll get to it today, but the point is, remember that if you see one of these lines indicating a chemical bond, each line stands for 2 electrons. They're being shared in that bond. Okay? So that was the covalent bond. I don't like that they got into that before I got to explain the metals, but no worries. So we said the metals can gain or lose electrons. They can form up in different ways, and they can lose various amounts of electrons. Like the hydrogen and the sodium, they always lose 1 electron. They always are Na plus, Ca2 plus, Mg2 plus, because they're very predictable. We know the easiest thing for it to do is just give away that electron. But in metals, it's not that simple because they're right in the middle of the periodic table. Let me go back to my periodic table real quick. And so really you can go all different kind of ways. You can do all different kind of combinations. And that's why knowing these other valence electrons are so important, because if you see a metal hooked up with one of these other elements, you can predict the way that metal is going to bond based on what these other non-metals, or say lithium, sodium, have done in the past. And what do I mean by that? Let's get into naming. So we know what an ionic bond is now. We know what ions are. We know what cations, anions. No, don't do that. Sorry about that. And this is basically all the same stuff I just said. So positive ions lose electrons. They're going to be on the left side of the periodic table, or also metals. So pretty much you can just say metals lose electrons. Okay? And then non-metals gain electrons. So fluorine, chlorine, bromine, all of those are in the non-metal group. They will accept electrons from other places. So I like saying that better, actually. Metals lose electrons, non-metals gain electrons. Oh, gosh. And so this is what we were talking about with the groups, right? That lets you predict how many valence electrons are there. Okay, so the study check is a good one to do. If I have 16 protons and 18 electrons, what is the chemical formula? So 16 protons, remember protons is the atomic number, so 16 is sulfur. And then it says, oh, wrong one. 18 electrons. So let me pull up my iPad. 18 electrons. I'm trying to remember and do all this at the same time. Okay, 18 electrons. So sulfur, we said, has 18 electrons. 1, 2, 8 on the next level. 3, 4, 5, 6, 7, 8. And then 18 electrons. So that'd be, what, 10 on this outer shell? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has 2 more electrons than it should, right? Because we only want to have the octet. So that would mean that sulfur is 2 minus charge. All right. So, and that was, I could have just done that by the fact that it has 18 electrons, 16 protons. If I have 2 extra negative charges than positive charges, then it'd be 2 minus also. Okay, so that'd be the easier way to do it, but I wanted you to see why there's 2 extra, because it went 2 over that octet that we would normally like to fill. Okay, so that is anions and cations and ionic charges. So now when you write the formulas for these ionic charges, uh, you put the cation first, the positively charged anion cation first, and then you write the name of the negatively charged ion last. Okay, then you drop the INE and put IDE on it. Okay, so NgCl2. Okay, let me go back to my iPad. Oh, y'all are on my iPad. Hold on. Sorry. Let me back up. We're starting to name ionic compounds. So simply, you just put the metal first and then the non-metal second. Okay, remember everything on the left side of the periodic table is a metal, and then after you get to metalloids, you transition to non-metals. So metal on the left, non-metal on the right. You also write out the names that way too. So your cation will be on the left, sodium in this instant, and then chlorine will be on the right. But I drop the INE and change it to IDE, and I make it sodium chloride. See right here. Magnesium chloride, magnesium plus chlorine, drop the INE, IDE, magnesium chloride. Now, if you need to know what the charges of these different atoms are, that's why I said you need to remember these trends. And they got this nice little table here, these trends for ionic charge, okay? So if I know that these atoms always have these certain charges, then if any of these atoms are paired up with something else, I might can determine the charge of the other atom. So let's do this one. Ionic formula for the compound barium chloride. Okay. So the first thing I want to do is figure out the number of valence electrons. So I'm going to go to my periodic table. Barium is in group 2. It has 2 valence electrons. And then chlorine is in group 7, so it has 7 valence electrons. All right. So barium has 2 valence electrons. And then chlorine has 7. So 1, 2, 3, 4, 5, 6, 7. All right, so now my job is to figure out what way this would hook up and make the most sense, okay? Oh, y'all can't see that. Hold on, let me fix this real quick. All right, that's better. Okay, so what way can I put barium and chlorine together that makes the most sense? Now, one thing you need to realize is I can have as many bariums and chlorines here as I want because I'm making a compound, right? So I know that barium wants to give away electrons because it's a metal. So let's say it gives 1 to chlorine. Now that fills that octet, and I still have 1 electron left. So I need another chlorine to give to. 1, 2, 3, 4, 5, 6, 7. And I'm going to give this one to that chlorine. Okay? So now my barium it's getting to its octet, right? I gave away those two and I made the other shell my outermost. But I needed 2 chlorines to do it. So now I'm going to write my chemical formula. Remember the metal first, non-metal second. So barium is what I'm going to write first. And I'm going to do both the chemical formula and the compound name. Okay, so the top one will be the name, and then this one will be the formula. Okay, so the formula is just the abbreviation, so I put Ba there for barium. Remember, I get this from my periodic table. Barium is number 56, Ba. Okay, and now my second one is chloride, or chlorine, right? But I have 2 of them. So on the name part, it's easy enough. When you're doing ionic bonds, you don't have to write anything except for these are separated. I just don't have room. You write chlorine, you drop the INE, and you make it IDE. Okay? So that becomes barium chloride. Now for the formula, I need to include the number of chlorines or the number of bariums that I have. So I had 2 chlorines. I'm going to write my formula like that. But either way, you follow kind of the same pattern. Metal on the left, non-metal on the right. Metal on the left, non-metal on the right. Since metals give up electrons, you could say that the cation is first and then the anion is second. However you want to think about it. Okay? But remember that you have to predict how many of each atom. Right? If I were to write just BaCl, it wouldn't be correct because Ba would still have 1 electron around its outer shell. And so technically it would be Ba plus instead of Ba2 plus, which is what it needs to be to hook up with the chlorines. Okay. Let's go back to PowerPoints. Okay, correct formula for each of the following ionic compounds. You just want to match charges, right? I want to have 2 plus on the, I want to have the same number of pluses and minuses on each side. Okay, so in order to make sodium and oxygen work, I need 2 sodiums to make 2 plus to match up with the 1 oxygen that has a 2 minus. So this will be number 2, Na2O. All right. Chlorine and aluminum. So aluminum has 3 plus charges. I'm going to need 3 minus charges to balance that out. So it would be 3 chlorines, AlCl3, number 1. Magnesium, make sure you can see. Okay. Magnesium and nitrogen. So this was a little tricky because 2 doesn't go into 3 and 3 doesn't go into 2. So you have to do, remember the least common denominator or whatever? The smallest number that 2 and 3 can both go into. That would be 6, right? So how many molecules of magnesium do I need to get to 6? 3, right? So 3 times 2 plus, let me do this one kind of on my iPad. Magnesium and nitrogen. MgN. Mg plus 2, N is minus 3. Is that right? Yeah. Okay, so I'll write mine a little different. But I need to know how many of these to make 6. I want to have plus 6 and minus 6 because that was my least common denominator. So that means I need 3 Mg's, right, times 3 equals 6. And then 2 N's because negative 3 times 2 is negative 6. Okay, so this would be my molecular formula, chemical formula, Mg3N2. That is number 3. Okay, so that's how you do that. Naming ionic compounds, we said, is just that easy. You name the cation first and then drop the INE on the second one or the ending on the second one and then replace it with IDE. So CaO would be calcium oxide. AlO would be aluminum oxide. MgCl2 would be magnesium chloride. Okay? And then here goes like kind of the rules. So you can go through and practice those. I'm not going to spend a lot of time on that. You are going to do that in lab though. So determining the charge is kind of what we were doing just a second ago, right? Let's do this one here, MnF2. So I know that fluorine has a predictable charge because it's on this row in the periodic table, group 7. Group 7 always has 7 valence electrons, and it always only accepts 1 valence electron, okay? Because we saw that several times now with chlorine. So if I have Mg and F, remember this has 7, 2, 3, 4, 5, 6, 7. But now the problem told me that I had 2 F's, right? Yeah, MnF2. So this is kind of a lot like that chlorine one that we just did. Except for it told me I had 2 F's instead of me having to figure it out. 1, 2, 3, 4, 5, 6, 7. All right. So now what it's asking really is, what is the charge of this magnesium? Okay. Now, if this magnesium gave away 2 electrons to fill this fluorine, then that means it's 2 electrons short of what it should be, and that makes the charge 2 plus. Okay? So that is why knowing that fluorine always accepts only 1 electron is important. It's why knowing that sodium always gives up only 1 electron is important, because it lets you predict these other things from that, right? I know that fluorine will only accept 1 electron, so if I had 2 fluorines accept electrons, then magnesium had to give up 2 electrons, okay? And when I write the chemical formula for that, because it can be in different, what we call variable states, I put a little Roman numeral 2 behind the magnesium. Or when I write it out, magnesium 2 fluoride would be the name of that one. And that's what they've done here. Oh, this is manganese, not magnesium, excuse me. Manganese fluoride. All right. Yep, so these are just the patterns, right? I told you that these all follow certain patterns. Some of these metals are very predictable. We know they're only going to be in a couple different states. When I say state, different charges. They're limited on what different charges they can have. So there's some practice. I don't want to stay on that too long. There's also a YouTube video on there. Polyatomic ions are ions that have different elements, but we use so often, or they have a unique structure, and we gave them their own name. So this is all over the place. At the top of this periodic table that I provided for y'all is a list of different polyatomic ions. It also has the charge here. So this is one of those being able to predict what it hooks up with, right? If something hooks up with sulfate, for example, make sure y'all are looking at, I'm at the top of this little periodic table. If something hooks up with sulfate, SO4 with a 2 minus charge, that means whatever hooked up with it had to have a 2 plus charge. So that's why they give you these, and you need to know these or have a table ready to use, because it's expecting you to be able to predict bonds or ionic connections based on these charges, or these polyatomic ions, I should say. And they also have their own name. So instead of saying chlorine oxide for hypochlorite, you need to say hypochlorite. Like I said, they all have unique structures or organization that requires them to have their own name and like even maybe a parentheses when they're in a compound. Okay, they're like a molecule within a molecule, if you will. All right, I don't want to get bogged down on that. Let's skip ahead, see what everything's polyatomic ions, naming still. I do a lot with the naming. I wasn't planning on doing as much with that. Okay, so this is kind of where I want to get to. Covalent bonds, right? We talked about covalent bonds in the chlorine. Let me make sure I still have a picture of that. Right here, right where they share the bonds. Now, another thing that we do in chemistry to kind of simplify this is we don't write out these orbitals, and we don't write out all the inner energy levels like I did here on this sulfur. We just do what's called a Lewis dot diagram. And what a Lewis dot diagram is the abbreviation. So what are we going to do? Let's do CH4. Okay, so CH4. All right. So CH4 is 4 covalent bonds between a carbon and 4 hydrogens. So when I'm writing out my atomic orbitals or whatever, I would have a bunch of these little rings or whatever, and then on the outermost shell I'd do 4 valence electrons, and I'd hook it up with a hydrogen which have 1 on its outer shell, like this. So we've simplified all that with something called the Lewis dot diagram. So what you'll do is you'll write the symbol of the element, so C for carbon's case. Now you start filling out the number of valence electrons it has in a clockwise fashion, and pretend that there's essentially 4 regions that you fill in. Okay, and each region can only have 2 electrons. So carbon, and now I'm going to start filling in. I'm going to go in a clockwise fashion, 1 at each of the poles, right? North, south, east, west poles. Yeah, until I run out. So carbon has 4. I go around in clockwise fashion. I put in 4. All right. I'm also going to write hydrogens out. Remember, this is CH4. I'll put this up at the top. A hydrogen here, a hydrogen here, and a hydrogen here. Okay. So now, when I combine these in a covalent bond, I'll just draw a line from one dot to the other, bop, 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 like that. Okay. Now, I did all that just to show you that when I actually write this, it'll be just a little straight line here, straight line there, and each one of these lines represents both of those electrons that I did here. Okay. So it's just more or less a simpler way of expressing compounds. Okay. So let's do another one. Let's do, say I hooked up chlorine with sodium. Okay. So remember, sodium is Na, and it just has the 1 valence electron. So I'm going to start on the right, and I'm going to put it here. But it really doesn't matter. You can start on any pole you want to. I do it there because I know where I'm going with this. All right, so now chlorine has 7 valence electrons. Let's do the Lewis dot diagram. 1, 2, 3, 4, 5, 6, 7. And you can only have 2 electrons in each little space. Remember, I did these little spaces on the poles. Okay. So now I've done 7 on that side, 1 on this side. I can't do sodium chloride because it's not a covalent bond. Hydrogen chloride. Let me change this. Hydrogen also has 1 valence electron. Okay? So now I can share those 2 electrons and make my compound. All right? But when I write this out in Lewis dot formula, I don't put that electron on the hydrogen. But I do leave the electrons around the outer edge of the chlorine. Okay? So all this just to say, remember that the line represents 2 electrons. One that's coming to the chlorine and one that came from the hydrogen. Okay? That's why they're covalent. 2 valence electrons being shared. Get all that off. So this is the Lewis dot diagram for HCl. Let's do a carbon with a carbon. Let's do water. Okay, H2O is water. I have 1 hydrogen here, 1 hydrogen with an electron there, and then oxygen has 6. So 1, 2, 3, 4, 5. Fill that in, 6. Okay. So now when I do my Lewis dot diagram, I need to predict where the hydrogen is going to bond. Remember, I can only have 2 on each pole, so I think they're going to bond down here with these solos. I'll go to this next page and I'll say O. 1 bonds to this H, 1 bonds to that H, and then I have my 4 valence electrons left over around the edge. Remember from here, 1, 2, 3, 4. I have to leave those on my diagram. So this is the Lewis dot structure. This is kind of how you write bonds. You'll see other things like double bonds and triple bonds. Let me do one of those. So oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. All right, so now I have 1 solo here and 1 solo there. On this side I have 1 solo here and 1 solo there. So how do I combine all of those? Let me flip this around and kind of face them at each other. So 1, 2, 3, 4, 1 solo there, 1 solo here. I'm going to flip this one around so that my 4 are on the outside. Now I'm going to hook the covalent bonds. I'm going to hook up 2 electrons on each side. So now we call this a double bond. And there's actually 4 electrons right here in this double bond. So when I write out my Lewis dot structure, we express that like 2 little lines. Okay? And you need to remember that there's actually 4 electrons being shared in that double bond. Another example, one further, is nitrogen. 1, 2, 3, 4, 5. Nitrogen, 1, 2, 3, 4, 5. Okay, so you can see where I'm going with this. It has 3 of these little solo regions. So I need to hook up 3 covalent bonds. And that'll end up looking like this. 1, 2, 3. Nitrogen, and then my 2 valents that are left over on the outside. So notice with all these that I'm filling the octet. All of this is to make sure that the octet is filled, right? If I have 6 electrons tied up in this bond and 2 on the outer edge, that makes 8 on this side and 8 on that side, right? 2 electrons right here, 8 on this side, 6 from the triple bond, and then 2 from the valence. Same on that side. If I go back to oxygen, there was 4 on the outside and then 4 tied up in the double bond. That makes a total of 8 on both sides. Go back to, so hydrogen we said can only have 2, but this 2 fills that, this 2 fills that, then the 2 from this, the 2 from that, 2 there make 8 total for the oxygen. All right, so all of this comes back to that, the 8 valence electrons, the octet rule. That's why all these bonds form. They're all based on these principles from the periodic table, right? The number of valence electrons. And so you can use this kind of like puzzle pieces. If you know some of this information, I can piece this together with some other information and come to a conclusion. right? That oxygen has two hydrogens attached to it, or that chlorine has a single bond. Sulfur has a double bond when bonded to itself. It works a lot like hydrogen, and that's because it has six valence electrons, like oxygen does. Excuse me, I said like oxygen does. Okay. So I stopped there for a second. I wanted to explain all of that. And we've done some diatomic molecules. We just did oxygen and nitrogen. We did chlorine earlier. We did the drawing the dot structures, exceptions to the octet rule. Okay, there are exceptions to the octet rule. Number one, hydrogen and helium, right? We said that those both only have the two electron outer shell, so it can only have two electrons, period. The others have to do with stuff below. Let me go to the periodic table. Stuff below this row. Okay, so 1, 2, 3, 4 rows. All right. Once you get down here, you open up another orbital. And this is not important for this class, but just so that you know what's going on. Once you get below this point, I guess technically it starts here because I can access this orbital on this row. I can access other energy levels that allow me to have more than an octet. Okay, so you will see some examples of that. I know we're going to talk about them in the lab. I'm trying to think how far I want to go with this. Yeah, I'll kind of do it as it comes. I don't really want to dive in. There are certain few, most of them are listed here where you can go up to 10 or 12 valence electrons, and that ends up forming different structures. So I'm not sure. We are going to talk about VSEPR, so I might talk about it when we get there. Okay, so we just did all this, the triple bonds. Molecular compounds, they have a little bit different naming. You have to put in how many of the atoms are in there. So basically follows the same rules. The more positively charged atom comes first, right? The one furthest on the left of the periodic table is written first, and then the one on the right is written last. Except for in this case, when you're talking about covalent bonds, you need to put how many there are because there can be multiple arrangements, different kinds of arrangements. In the ionic bonds, it was predictable because I know that sodium only gives up one electron. In this, there can be variation. Okay, so we have to say if there's two, we use the word nitrogen, dihydrogen. 3 is tri, 4 tetra, 5 penta. I can't remember 6 hexa. I think I'm trying to find the table in the text. It might be good to have like a little table that reminds you of these little prefixes. And I'm thinking that you have one in your text, but I don't see it. Nope. Let me pull y'all over here so in case I find it. Text. Lewis dot structures. We've been touching on that. Yep. Go. Dipole. I'm glad I saw that. I need to show y'all that. Don't see the table that I thought I would. Oh, here it is. So page 186, prefixes and name of molecular compounds. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. All right, so that's that. Here's some examples sulfur dioxide, sulfur hexafluoride, sulfur trioxide. So it's basically the same rules, but you just need to add the prefix to let them know how many is in, how many of each atom is there. Okay? So dipoles, I'm glad I saw that because I think I missed it when I should have talked about it. Let's go back to this iPad real quick. All right, so a dipole, remember when I talked about the NaCl and this bond forming right here because they have different charges. Okay, so this is, and you've heard me say poles a couple times. So think about a magnet, right? A magnet has a north pole and a south pole. And the south pole only attracts to the north pole. If you try to stick the north together with the north, they repel each other. So atoms work the same way, all right? But what happens is they will create a dipole on their own, okay? And so what does that mean? Okay, so remember that I have all these electrons floating around the outside, all right? Well, if I come in contact, let me find something that has a charge on it. Might need to make one. That's not going to work. I'm going to just make my own. Okay, so I'm going to do this NaCl again. The positive charge over there, negative charge over here. I'm just going to use this to illustrate what a dipole is, and then we'll talk about what it means for covalent bonds, okay? So a dipole is where I have a molecule and it has, just like we said, different poles, right? You can imagine this is the North Pole and then this is the South Pole. So if there's anything else out in this world that has poles on it, say MgCl2, right? I'll actually write it like the molecule. Hold on. South pole, Mg, and then it has two Cl's. I'm going to write it like a covalent bond, but it's not a covalent bond. But it does let me show that this magnesium is more positively charged, this chlorine is more negative, this chlorine is more negative. Okay? So it creates what we call the dipole, where one side of the molecule is positively charged, the other side is negatively charged. All right, and so when it aligns next to this NaCl, the positive will pull towards that chlorine, and these chlorines will pull towards that sodium. So it makes a predictable pattern of charges, right? The positive hooks to the negative, then that negative will hook to the positive, then that positive will hook to the negative. So now this happens in covalent bonds, but it happens between elements that are surrounded by the same thing. Let me explain. Let me find if it has an example of one I want to use. Where was that dipole section? Okay, these are good. Yeah, hydrogen chloride. This one will work. All right, let me do that one. Okay, so the hydrogen is just like the magnesium in that it always gives up an electron. So this one's always going to be more positively charged. The chlorine always accepts an electron, so it ends up becoming more negatively charged. Now, if I were imagining that these electrons like have an energy about them, the energy force might look something like this, right? All of the electron or the negative atmospheres on this right side. I need to make it prettier than that. HCl, let's do it like this. Little positive charge, big negative charge. So it's more or less like this. Okay? So all this over here is a bunch of negative charge, all right? And then over here I got this little positive charge. Well, that will influence everything else around it as well. So say I have a carbon and a bunch of hydrogens here, right? So remember, all these hydrogens are a little positively charged, little positively charged, little positive, little positive. The carbon actually has a lot of extra electrons on it, so it's kind of negative. This is not a best example. Let me do something else. Let's do something that has the same charge. I think that'll illustrate it better. So oxygen. Remember we said oxygen has a double bond? So there is no dipole here. These both have the same amount of negative charge. But what happens is, because it's interacting with something near it that's positively charged, it tends to pull more negative charge from the other side. So this side, whichever side is closest to this hydrogen, ends up becoming more negative than this side. This side becomes a little more positive because it's further away. So like I said, you have this predictable pattern where you have a plus charge, the closest thing to it will be a minus charge, then on the other side of that will be a plus and a minus, and so on and so forth. That's how dipoles interact. Okay, they kind of pull the charges away from each other, and it can kind of tip the balance of charge in a molecule when they sit next to other molecules with dipoles. Okay, so that's how that kind of influences, not necessarily bonding, but it can influence bonding as well. All right. So electronegativity, we haven't really talked about this yet, but it is essentially how much something wants an electron or holds on to an electron, okay? And so in a certain case, it's kind of the opposite of the valence electron. Let me show you what I mean. So go to your periodic table, and we'll see that lithium, sodium, potassium, remember they're all in that group 1. They all really want to give away an electron. They don't want to hold on to it that bad. So its electronegativity is low. It doesn't want electrons. It typically is more positively charged. It wants to give up electrons. So if I look at my electronegativity chart, oh, you're already looking at it. You'll see that all of those have a very low electronegativity. Things that want to take electrons, like the fluorine, chlorine, bromine, the halogens that have 7 valence electrons and it really just wants to get one more, they have a very high electronegativity. So that's why this pattern follows that trend. Left to right, it's essentially just how much does it want to be an anion, right? How much does it want to take on more electrons? These ones on the left don't. It'd be much easier for them to give away the electron than to take it. So they have a low electronegativity. This electronegativity is also used to determine whether or not you're actually dealing with a covalent bond or ionic bond. If they have a large separation in electronegativity, then you're probably looking at an ionic bond. And if they have a very close value, if their electronegativities are very similar, then it's a covalent bond. Okay? And there, I think there's a chart somewhere. Oh yeah, here it is. So 0 to 0.4, the difference in electronegativity is the electrons are shared equally. It's nonpolar. When it has, so this one right here would be like the polar covalent, where it has a large negative portion and then a smaller positive portion, or vice versa. They would call that polar covalent. And then when they don't share electrons at all, they would just completely give it away to the other. That's ionic. And you can tell all this by the electronegativity difference. So the way this works is you go to the electronegativity chart, and you have 2 atoms that are bound, say the nitrogen and the oxygen. and you say 3.5 minus 3 equals 0.5. And then I come down here, 0.5 is pretty much polar covalent, okay? And the oxygen would be more negatively charged, and the nitrogen would be this little gamma positive. Okay, the gamma is this little symbol here. That's actually not gamma, what is that? Epsilon or something. Alright. So the polarity, we talked about that. That occurs because one thing is more negative, and then so it kind of pushes the charges around, and so you see this dipole where one side's negative, one side's positive. Whichever atom has the highest electronegativity is the more negatively charged region. All right. I don't know. I think some of your master in chemistry will have some of that. All right. So the last thing we're going to talk about today is the VSEPR model. Okay. And I know this is, like I said, this is a lot of stuff and a lot of information. That's why I put all those YouTube videos on there. If if you stopped the video and then came back and don't know where you're at, whatever, whichever part you're having a problem with, you can email me whatever questions you have. But those other videos are there to supplement that. Okay, they touch on the same things that I'm talking about in a different way that might make it click more easily for you. So use that if you need to, for sure. Email me if you want. I'm always here. John Lewis structures, we're good on that. This formula, there is this formula here to determine the total valence electrons, but as I said, it's essentially just adding up the periodic table, right? So if I have PCl3 here, I can just go to my periodic table. Where's it at? Periodic table, find P is number 15, group 5. So it has 5 valence electrons. Cl has 7. So 3 Cls, that means 3 times 7 will be 21. 21 plus the 5 from phosphorus equals 26, right? That's all this little calculation is doing, 26 electrons. All right. And so then when I go through and start bonding, I want to make sure that when I finish my Lewis structure, I have 26 electrons. 2 in each bond, so 2, 4, 6. And then I count up all the other valence electrons. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay? So that's how you kind of check yourself. If you didn't match up right, that means you don't have the right number of double bonds in there. There might be a double bond, which that'll shift the numbers around because it takes away one of these pairs of valence electrons. It essentially reduces the total valence electrons by 2. So if you're 2 over, you might need to add a double bond. If you're 4 over, you might need to add 2 double bonds or 1 triple bond. Okay, so that's how you can kind of check your valence electrons or your Lewis dot structures. And I know I just jumped around, but the VSEPR model is really what I wanted to talk about. So when you do your Lewis structures and you figure out how you've combined them, you need to pay attention to those numbers of electronic regions. So when I was talking about them earlier, I referred to them as poles. But now that we have a meaning of dipole, we need to talk about these in terms of electronic regions. Here's one that I circled. Remember, I circled that hydrogen. Those 2 hydrogens is a different region. And when I do my Lewis dot structure, I do it in regions as well. So this is, let's do CH4. Okay. So now we need to imagine this in 3-dimensional space. How can I do this? Let me go to just me. All right. Oh, let me find something I can do this with. 1, 2, 3. That's not this carbon here. This is the carbon. I'm getting my little model together. I got a little model thing here. Hopefully I can use to kind of show y'all what's going on. Alright, so we've been drawing these structures on paper, and I think it's important that we remember that these structures are three-dimensional, right? Atoms are three-dimensional. And so we also need to take into account what their shape is when all these things happen, when all these bonds form. It's important for us to know the different shapes and angles and whatnot, because that will also determine how they bond, how they hook up. Some of these just don't fit. 1, 2, 3, 4. Okay. So I've just drawn this molecule here in Lewis dot formula. Okay, so 4 hydrogens around a carbon. On a 2D plane, it looks like a square or a diamond. Now, imagine if I need to do this in 3 dimensions, but I need to have all of those hydrogens the same distance apart. Right? How would I do that? You form a pyramid, is essentially what you do. If I think about it, all 3 of these sides are equal distance apart. How do I turn it? Yep. I can't turn around into the camera. So all 3 of those hydrogens are equal distance apart. I'll flip over to here, turn to there. They're all the same distance apart. So in this way, I've created the least amount of resistance, right? Remember, these all have the same charge too. So if they were trying to butt up to each other, they repel just like a magnet would, north to north, south to south. These can't be right on top of each other because they're both surrounded by electrons. So once I start getting them in real tight, they start pushing back away. So they need to be as far away from each other as possible while still making these bonds, okay? And so this is what we end up coming up with. This is called a trigonal pyramid, right? Three-sided bottom pyramid, okay? No, tetrahedral, excuse me. The trigonal is for 5. Tetrahedral. So this is what the Vesper model is saying, essentially, is however your setup is, they need to arrange in such a way that reduces the pushes and the pulls on the atoms. Excuse me. I've also included a YouTube video for this. Now, this one is a lot easier to do in person, where I can work with these models and kind of draw it on the board. Let me pull up the text and see what they do with it. This chart is going to be the most important thing, though. Okay, this chart here. So when you're talking about Lewis dot structures and molecular structures, let me go back to the iPad. You have to incorporate the electronic regions and the molecular regions. So that table might not actually be the best. It's not how I remember the table being. Okay, so let me do water, for example. Okay, water is HO and then H here, but it also has the 4 electrons on this on its outer shell. Okay, so if I'm going to make if I want to try to predict what this will look like in 3D, I need to, first thing I have to do is figure out how many regions I have around it. Okay, so 1, 2, electron pairs count as 1 region. 3, 4. Okay, 4 electronic regions. So I'm going to go to my table and I'm going to look for something, electron groups 4. Okay, so the electron group geometry is tetrahedral. Now there's only like say 5 different shapes that you need to know. There's the tetrahedral. Where's the shapes at? Okay, so this is linear, trigonal planar. Why does it keep doing that? Stop jumping. Trigonal planar, which planar means it's flat. So this is, I'll show you when I pull back out my models here in just a second. Tetrahedral is this one here, the one that I showed you with my model, right? That's the tetrahedral. So 4 electronic regions around a central atom. That's pretty much all carbons are going to be tetrahedral. And then the others are trigonal pyramidal and octahedral. Okay? I don't see an octahedral here, but that's good because I don't want to do it. All right, so now back to the iPad. I just did that to show you there's like 5 different shapes that you need to know for electron geometry. The others are a little tougher and you got to kind of imagine. So we said the 4 regions here make it tetrahedral. Now I'm looking at the molecular shape. When I talk about molecular shape, I only highlight the ones with atoms. So there's 2 molecular regions and 4 electronic groups. Okay? So go back to my table here. 4 electron groups with 2 bonded atoms means that my molecular shape is bent and it comes out looking like this, right? So that's, let me see if I have one. This would be the water molecule. Okay, H2O is an example of this, right? We saw in the oxygen has 2 extra electron regions that you can't see. If I was going to add, let's just say I add these little sticks to make electrons, but there's not really atoms there, it looks like that tetrahedral without the atoms, right? This was my tetrahedral. This is my water, right? But this one has atoms and this one doesn't. Those 2 little poles are just 2 electrons, 2 valence electrons. But I put them there to say they influence the shape of the atom. Even though there's not an atom there, the fact that these electrons are pushing away from each other influences where these atoms do connect. So that's why it's important that you know this. Let me see. Say this one has 1 less atom and it's like this. This is called trigonal pyramidal, and it would be 3 atoms bonded with 4 electron groups. So back to your chart, 4 electron groups, 3 bonded atoms, 1 lone pair of electrons, which is this little stick there, will give you a trigonal pyramidal shape. So like I think NH3 is this, and that's what it kind of looks like. Yeah, so there's all different kinds. There's only like 5 different main shapes. You start with that. Start with the main shape. It's either got to be trigonal planar, linear, tetrahedral, or trigonal bipyramidal, whatever that the 5 one, and then octahedral 6. I might do a better chart. Let me see if there's a better chart on the internet. Let's see, Vesper chart, images. It's not very good. It's not very good. It's not bad. See, so you're gonna have to see which one of these you like the wording behind. This is the simplest one for me. Okay, so linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. It's all based on the number of electron regions around your Lewis dot formula. And then it gives you a bond angle. I'm not really concerned about that. More or less, it's just the shape. Okay, so you'll need to be able to use one of these charts to tell you what the shape of the molecule will be. All right. And like I said, I don't mind if you print this up and have like a little cheat sheet. Here's a good one here. So it has the lone pairs of electrons, the total number of electrons. It's even got like IF7. I've never even seen that. Yeah, this one's real good. But so if you'll just go through and then find which one has your number of electron pairs and then the number of lone pairs, and then it'll tell you what shape it is. So there's the bent, tetrahedral, seesaw is one that I've seen, T-shaped I've seen, octahedral, square pyramidal, all of these ones you could see. So I like this chart the best, I think, so far, but I'm sure there's even better out there. All right. Yeah, I'm not going to get too much more into that. We'll work in this in lab. This is actually part of the lab too. So let's see if there's anything else I want to touch on before we get out of here. Intermolecular forces. I do need to mention that. And, yeah, so just with the intermolecular forces, um, hydrogen bonding, and it really has to do all with those charges, the difference in charges that we were talking about earlier. Dipole-dipole interaction, so that's where a positive from one molecule interacts with a negative with another molecule, and it starts to shift that balance of charge. Um, what's another one? That the shifting of the charge is what causes the polarity. Polarity is just having more negative charge on one side of the atom of the molecule than on the other side of the molecule. Hydrogen bonds. So hydrogens tend to form bonds with nitrogen, oxygen, and fluorine. Uh, Mostly just oxygen and nitrogen. So if there's a hydrogen around oxygen and nitrogen, you can go ahead and expect for the hydrogen bond to occur. That's what happens with water and is what makes water stick together kind of as you pour it out, right? It doesn't just split up into all the different atoms. They kind of have attractive forces that kind of keep them held together and move as one fluid, so to speak. So that is caused by the hydrogen bonding. The fact that hydrogen is in the molecule and oxygen as well, they'll arrange where the oxygen sits on one side of the oxygen. Hydrogen, oxygen, hydrogen, oxygen, plus minus, which we've touched on that as well. Nitrogen does the same thing. Nitrogen is more negatively charged, so you get this series of bonds where the hydrogen stacks up with the nitrogen, and it gets positive, negative, positive, negative, positive, negative. Okay. Dispersion, London dispersion forces, that only occurs in hydrocarbons. Longer hydrocarbons have more dispersion. Dispersion is kind of a unbalancing of the charges, right? As it gets real long, some of those charges can end up on one side of the molecule or other, and then that creates these kind of interactions with other long chain molecules, and so you have essentially it's like an ionic bonding that occurs on a very small scale between very long molecules. And I guess that's all you really need to know about the different attractive forces. The more attraction they have, the higher melting point. That's all that's going to say. Um, okay. So yeah, look for your Mastering Chemistry. We're already at an hour and 20 minutes, so yeah. Try to go as quick and as simple as possible. But like I said, I got the backup videos on there. Let me know what you need help on. I'm gonna, if you the Vesper was your concern, we're gonna do a lot more of that in lab, and there's also more videos on YouTube about that. Um, it can be complicated, and I don't want to do too much that you're not gonna have to worry about. Okay, it's easiest if you just use the chart, learn to use the chart, learn to do your Lewis dot diagrams, and then use the chart to tell me what the shape is. Okay, because you don't have any of these little figures here, and usually that's how I can kind of show you. I can show you a lot better than I can tell you. But to sit here and walk through each one, we might do that in lab, but I'm not going to do it here in lecture. So that's it for today. Look for your master in chemistry, and I'm doing the lab next. So if you're waiting on that, it'll be posted in just a little while. All right. Bye, y'all.